So back to our first page, we've done some very complicated concepts here, and we've accomplished a lot. We've described how the circulatory system works with oxygen binding tightly to hemoglobin in the lungs. That's its job. Hemoglobin carries that oxygen out to the muscles, and then hemoglobin binds oxygen weakly there, and the oxygen jumps over to the myoglobin, which binds oxygen tightly all the time. All of this is set up to have directional transport of oxygen. We went through the whole model about how hemoglobin can go back and forth between the tense and the relaxed state. I'm going to go ahead and put those down. You can if you want. And there's some important principles there for us to understand. Believe it or not, we're going to make this even a little more complicated because hemoglobin is much more sophisticated than what we've described it as already. Let's make a note. Hemoglobin delivers more oxygen to active muscles. How does it know to do that? Well, that's what we need to talk about. Second of all, hemoglobin adjusts to altitude. You may know that if you go to high altitude, you have some problems breathing because oxygen is not being delivered well. And believe it or not, hemoglobin can adjust and make that easier for us. So how does all this happen? Well, let's continue on to this page. We said earlier that the tense state and the relaxed state are in equilibrium as hemoglobin goes throughout the body. And we said that tense state is weak binding, relaxed state is tight binding. Now, how does the hemoglobin know to be in the tight binding state over here or the weak binding state? All right, let's set up a little chart. Let's talk about lungs and muscles or tissues. And then let's talk about various conditions that happen. We already talked about one of them, the oxygen partial pressure. We know that it's high in lungs and low in muscles. And we said that oxygen binding to hemoglobin stabilizes the relaxed state and makes it easier for other oxygens to bind. And when it falls off, it tends to go back to the tense state and makes it easier for other oxygen to fall off. So that's one condition, but think about it. Maybe you know this from general activity or physiology classes. What are the other signals that we have, chemical signals, in active muscles? What do we know about active muscles? How do they behave chemically? Maybe some of you know that CO2 levels are going to be higher in active muscles than in the lungs. Why is that? Because CO2 is produced when we burn up our fuels, and we build it up, and it has to get exported to the lungs where it gets breathed out, and therefore there's less in the lungs because it's gone and more in the muscles. You may also know that when you use a muscle a lot, you tend to build up acid. That's protons. Maybe you've heard that lactic acid tends to build up. So protons tend to be higher in muscles, and you actually have a lower pH in muscles. And they tend to be a little bit lower or more normal, pH 7.4, in the lungs. So these two conditions that are different in active muscles compared to regular muscles or the lungs, it makes up what we call the Bohr effect, B-O-H-R effect. And that is going to be described on the next page a little bit. In our two-state concerted model, we said, let's write it again. It's so important. T-state, weak O2 binding. R-state, tight O2 binding. And the behavior of hemoglobin as it passes through the body is going to be determined by which way this equilibrium shifts. So let's say it again. When you have oxygen in the lungs, there's a lot of it there. It binds and helps other oxygens bind because it shifts to the relaxed state. That oxygen catches a ride out to the muscles, and when you get there, there's low oxygen, so they tend to jump off because we switch back to the tense state, and it's weak binding. But here's the deal. There's also CO2 and protons out here, and because there's a lot of CO2 and protons, they hop on and they ride back on hemoglobin. And when hemoglobin gets back to the lungs, the CO2 hops off into the alveolar spaces and goes out when you breathe out, and protons hop off as well. So hemoglobin clearly is going to be carrying oxygen out to the tissues, but it's just as important that it brings CO2 and protons, but particularly CO2, back to the lungs and then out. So that's an additional function of hemoglobin. And notice this though, with the two-state concerted model, let's say the next axiom here, anything that binds and stabilizes the T state or tense state makes it harder for oxygen to bind. And what we can say now, let's put it down here, CO2 and protons bind and stabilize the tense state. They have the opposite effect of oxygen. So when protons and CO2 bind, they shift hemoglobin back to the T state, and that causes more oxygen to fall off because oxygen doesn't stick well to the T state. Okay, let's finish this video off with a thought exercise here. Let's go down and let's talk about what happens with active muscles. Okay, I went ahead and wrote in our standard oxygen saturation curve for myoglobin and hemoglobin. Notice in green I put hemoglobin at pH 7.4. And here's my question for you. How does the curve change in active muscle? And by active muscle, let's just say pH 7.2. If you have a very active muscle, the pH will drop because you're making a lot of protons and also CO2. How will it look? Let me give you this hint. The cooperativity effect of hemoglobin is the same, but the protons are going to push it to the tense state, and that's going to change your curve. Let's see if you come up with a curve that makes sense. Pause and let's see how it goes. Okay, did you listen to my clues carefully? I said in the presence of protons at say pH 7.2, the cooperativity stays the same. What that means is the shape is going to be the same. It's still going to be sigmoidal. But I said it pushes it to the tense state, and we know that when it's in the tense state, it binds oxygen weaker. What happens when hemoglobin binds oxygen weaker? It shifts. Now, do you remember, does it shift to the left or to the right? Hopefully you guessed that it shifts it to the right. And this is going to be hemoglobin at pH 7.2. See, it's still sigmoidal, and it's shifted to the right, which means it has a higher P50, weaker binding. Here's another thought question for you to finish up. Analyze the gaps between hemoglobin and myoglobin at pH 7.4 and 7.2 and tell me, what does that tell you about the delivery of oxygen in those two conditions? Pause, see if you can sort that out. Okay, when we analyze the gaps, let's put in a gap here. Say that myoglobin is winning against hemoglobin 7.4 for sure. That's in a normal muscle. But notice the gap is actually bigger between myoglobin and hemoglobin at pH 7.2. That means for active muscles, the gap is bigger and more oxygen is delivered. Myoglobin wins even better in active muscles and gets more oxygen. That's set up to have more delivery when needed. This has been a long video. Let's stop it there.